Okay, here we are at Part C of the January 2020 New York State Chemistry Regents exam. Now, this comes obviously at the end of the exam. This is going to be questions 66 through 85. This is for some students the make or break as far as passing the Regents or doing well on the Regents. You don't want to skip these type of questions when you're practicing and getting ready. What you're going to see is you're going to have typically a reading passage or a picture or a graph, and then you have questions from all parts of the chemistry course that you have to answer. These are all short answer type questions. We're going to get to it. Hey, and if you don't mind, hit the subscribe button if you haven't already. Leave a comment down below if there's anything that you want me to address as far as chemistry for the channel. All right, so let's get started. We have a reading passage here about Sir William Ramsay, and you don't want to skip these. Always go ahead and read them pretty closely. We're going to get right to the questions here. And in 66, it says compare the reactivities of nitrogen gas and argon gas based on Sir Ramsay's experiment using magnesium. Obviously, that means you need to go back into this reading passage to see what Sir Ramsay did when it comes to magnesium. Nitrogen and the magnesium reacted, and it formed magnesium nitride. However, when it came to an unreactive gas like argon gas, nothing happened. So argon did not react, and the nitrogen did. In 67, compare the density of nitrogen gas to the density of argon when both are at 298 K and 101.3 kilopascals. All right, let's go back into the passage and see what happens. Well, it tells us that there were different densities, but not enough, it looks like here, maybe to be able to compare. That means we need to go to the reference tables. So let's do that. Okay, here we are at reference table S. A lot of physical properties always for all elements. If you take a look, also the names and the correct spelling for elements. It's a good table to keep remembering as you're taking a test. All right, so I circled the density of nitrogen and the density of argon, and don't let the small numbers fool you. Argon is more dense than nitrogen. There's your answer. For question 68, state in terms of valence electrons. You got to be careful with these part 2 questions, whether it's from B-2 or part C. Anytime it says in terms of, you better address that in your answer. Otherwise, you can make a completely correct statement but get no points. So we're talking in terms of valence electrons, why the noble gases that Sir Ramsay discovered have similar chemical properties. Well, in terms of valence electrons, let's go to the periodic table. When it comes to periodic table, remember these columns or group numbers are important. Our noble gases are group 18, and with the exception of helium, which only has 2 valence electrons, all the other noble gases have the same number of valence electrons, which is 8. And that's why they have similar chemical properties. The last one here in this group of questions, 69, it says state the trend at standard pressure of the boiling points of these noble gases as they are considered in order of increasing atomic number. Neon, krypton, xenon. For boiling points, once again, we're going to reference table S. I just circled the noble gases, right? This is going down the group, neon, argon, krypton, and you see for boiling points, they are increasing as you go down a group. And by the way, when you are working on practicing questions and the exam itself, mark up the reference tables. They're your reference tables to use. So take advantage of that so you don't miss anything. So we got that trend down, right? That increasing atomic number, increasing boiling points. We're going to move on here to questions 70 through 72, and here we go. All right, again, reading passage. We're going to go right to question 70, but you should always read it over first. State how many times greater the hydronium ion concentration in the lake water is than the hydronium concentration in the sample of normal rainwater. I go back to the reading passage. Normal rainwater is 5.6 pH. Lake water is 4.6. While the pH is one number lower for lake water, remember what that means. That means the hydrogen ion, also known as hydronium ion concentration, increased by 10 times. So with each number, as you go down in pH, it increases the acidity by 10 times. That's our answer. In 71, we're stating the color of methyl orange in a sample of normal rainwater. Our normal rainwater is 5.6. We need to go to the reference tables again and check that out. So let's do that right now. Methyl orange is under table M for common acid-base indicators. We're looking at methyl orange. It happens to be the first one right here. And we're talking about a pH of 5.6, which is higher than 4.4. Starting with 4.4 and higher, what color are we going to have? We're going to have yellow. That's our answer. 72, once again, if you haven't figured it out, we keep going so far in Part C a lot to the reference tables. We're going to Table G and describe what happens to the solubility of SO2 as the temperature increases from 10 to 30 degrees Celsius at standard pressure. Table G, solubility curves. I'm going to scroll on down. Here is SO2 at the bottom. So we're following the SO2 line, and I think it was from 10 to 30 degrees. And notice what's happening. The solubility is decreasing. That's our answer. Let's go back. We're heading now to 73 through 77. All right, we have an equation here with acetylene gas and oxygen. First question, write the empirical formula for acetylene. Well, here it is. We had to, first of all, identify what the compound formula is, which is C2H2. Remember, empirical formula is your lowest whole number ratio for a compound. I can divide both by 2, and we end up with an empirical formula of CH. Alrighty, let's go on to 74. In your answer booklet, use the key to draw a particle model diagram to represent the phase of O2. Your response must include at least 6 molecules. Now, they're not kidding here. If you drew 5 or 4, you didn't have at least 6, you wouldn't get credit. And also notice you're talking about oxygen. It's a gas. And what do you know about gases? The particles are spread far apart. Now, I don't have the answer booklet, so we're going to go to the answer key just so you can take a look here at 74. Okay, so oxygen is O2. Of course, you have to remember it is a diatomic molecule, right? Which means it's 2 atoms of the same element. So you see the double circles, and sure enough, I have 6 here. So this is what we would be looking for. Now, in 75, it says to balance the equation in your answer booklet for the reaction between acetylene and oxygen using the smallest whole number coefficients. I'm going to just go ahead and use the equation that's right here. It would be the same equation in the answer booklet, but just spaces in front. What I always tell my students, real simple, start with anything but oxygens and hydrogens. And since you have O2 alone, you want to do oxygen last because you can put any number in front there and we can figure it out. All right. I have 2 carbons on the left. I only have 1 on the right, so I'm going to put a 2 in front of CO2. Then I go to hydrogen. I have 2 on the left. I have 2 on the right, so life is good. Where it gets a little tricky is with oxygen. I have 2 on the left, and I have 2 plus 1. I have 2 times 2, which is 4, plus 1, which is 5 on the right. It's hard when you have an odd number, but I can tell you right now what we can do is we can go through this equation and double up the C2H. I have 2 times 2, which is 4 carbons on the left. I have 1 on the right. I'm going to put a 4 in front of CO2. I go to hydrogen. I have 2 times 2, which is 4 on the left, and I have 2 on the right. I'm going to put a 2 in front of water. Okay. Then as far as oxygen, right now I only have 2 on the left. On the right, I have 4 times 2, which is 8, plus another 2, which is 10. that works, because what that means then is I just need a 5 in front of O2. Here is then the balanced equation, right, with the smallest whole number coefficients. So when you get combustion reactions like this, if it doesn't work where your oxygens are balancing, just go back and double up that fuel, in this case, the acetylene gas, and you should be able to do it. For 76, it says determine the mass of 25 moles of acetylene, and they give you the gram formula mass. Well, reference table T is going to have the formula. Let's go there so you know where it is. Here we are at reference table T, and sure enough, we need this formula here. We have our moles, they gave us the gram formula mass, and we're going to solve for the given mass, or not the given mass, but what we're calculating. Let's go back. All right, so what I did was I went ahead and put my 25 moles in, and I got my gram formula mass of 26, and I got to solve for x. Now remember, this is like a proportion, folks. 25 is 25 over 1. I'm going to cross multiply, right, and then divide if I have to, but x times 1 is x. So x is equal to 25 times 26, which is 650 grams. That's our answer for 76. All right, one more in this cluster, and that is explain in terms of bonding. We got to remember, we got to make sure we address that in the question. Why the hydrocarbon gas used in the cutting torch is classified as an alkyne. So the hydrocarbon gas C2H2 is classified as an alkyne, and we have to explain in terms of bonding. Now, if you recall alkyne or the YNE ending, you might remember that it has a triple bond between the carbons, and that's exactly what they're looking for. But let's say you weren't sure, you wanted to double check. Yes, you can go to the reference tables. Let's do that. Here we are, reference table Q. And there, the last line are my alkynes. In fact, there's acetylene. And what do I know? I got that triple bond between carbons. That's what they were looking for. Let's keep going. We are checking out questions 78 through 82. We have some reading here, and we also have a chart. Let's get to it with 78. Compare the thermal energy of a 10-gram sample of water at 25 degrees Celsius to a 1,000-gram sample of water at 25 degrees Celsius. Now, I'm sure your teacher, like me, keeps reminding you that temperature is a measure of kinetic energy. And since they're both at the same temperature, you might say, well, they got the same energy. But you got to be careful. Kinetic energy, energy of motion, that's going to be different than thermal energy. Thermal energy is the transfer of energy, right, from hot to cold. And so when I have a 1,000-gram sample, that has more energy to transfer than a 10-gram sample. So therefore, the 1,000-gram sample has a higher thermal energy than the 10-gram sample. That's a tricky question. Typically, there's one on the test, and I think I found it in 78. Let's move on to 79. For 79, what happens to the potential energy of the molecules in a solid sample of hexane at negative 95 degrees Celsius as heat is added until the hexane is completely melted? Well, anytime you're going through a phase change, in this case solid to liquid, the temperature remains constant. In this case, the potential energy would be increasing for 79. Okay, for 80, it says determine the vapor pressure of water at 69 degrees Celsius. Now you might think, oh, I have a calculation. No. We have a vapor pressure diagram on the reference tables. Let's go check it out. We got to remember it's water at 69 degrees Celsius. Okay, this again is one of those places where you want to mark up the table. And we said it was 69 degrees Celsius. This line is the 70 mark. So it's just about on the line. And then you hit the water curve and you go over. And it looks to be, let's see, we're going up by tens for the y-axis, 10, 20. It's around 30 kPa. Sounds good to me. Before we get back to the questions, I just want to show you something here on the answer keys that us teachers get when we're grading. First of all, for 80, they did give us a range. So as long as you're falling somewhere in that range, so 28, 29, or 30, you would have gotten the credit. Then you see for the rest of these, including the next question we're going to go over, that it says acceptable responses include but are not limited to. Just make sure that you're answering in terms of what you're being asked. All right, so with that, let's look at 81. Explain in terms of molecular polarity why hexane is nearly insoluble in water. Well, hopefully you remember water is polar. Hexane then must be nonpolar, or they have different polarities if you want to say it that way. But really, to nail it, water is a polar molecule and hexane is nonpolar. Let's go to 82. Explain in terms of molecular formulas and structural formulas why 2,2-dimethylbutane is an isomer of hexane. In terms of molecular formulas, let's take one at a time. 2,2-dimethylbutane. Probably makes sense to draw the molecule. But means 4, so you have a 4-carbon chain. 2,2-dimethyl means that on the second carbon, you have a CH3 group, and then, of course, you have hydrogens filling everything else in. I'm just going to draw them in as lines. If we add it up, 1, 2, 3, 4, 5, we have 6 carbons, and we have, I'm going to start here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 hydrogens. When I'm dealing with hexane, hexane is 6, C6, and hexane H. Remember, there's a reference table for alkanes. It's CnH2n plus 2. In other words, the N is the number of carbons. 2 times 6 is 12, plus 2 is 14. So in terms of molecular formulas, they are exactly the same. But in terms of structural formulas, they are different. And that's really all you have to say, but I just wanted you to see it. Hexane, instead of having these 2 branches you see with the dimethyls, hexane would just be carbons straight across, 6 of them. And then all your hydrogens filled in. Okay, even if you have a bend in the molecule, that doesn't count. So 1, 2, 3, 4, 5, 6. And then you fill all the rest up with hydrogens. All right, we've hit almost the end here, folks. We got 83, 84, and 85, and we're done. So in this case, notice you have, of course, a diagram. You're talking about an electrochemical cell. This is actually an electrolytic cell because we have energy being used with our battery to force a chemical reaction to happen. And let's take a look at the questions. Question 83, state the change in oxidation number that occurs for oxygen in the overall reaction. Here's our overall reaction. Oxygen in water is a compound, so it's bonded with hydrogen. That makes oxygen's oxidation number a -2. When oxygen or any other element is alone, the oxidation number is 0. We're going from -2 to 0 for 83. For 84, compare the number of electrons lost by oxygen to the number of electrons gained by hydrogen in the overall reaction. Well, in order for it to be a correct overall reaction, the number of electrons gained must equal the number of electrons lost. That's all you need to know. You didn't have to figure anything out here. It's a little misleading because you have a 4 here and a 2 here, but remember you have to combine and balance the reaction. So they're equal in 84. Finally, question 85. Here we are. Determine the number of moles of hydrogen gas produced when 0.0004 moles of oxygen gas is produced. All right, this is just a mole problem. We're looking for the moles of hydrogen gas. That's our X. We have 0.0004 moles of oxygen gas. The coefficient in front of O2 is 1. The coefficient in front of H2 is 2. What am I doing? I'm cross multiplying. X times 1 is X, and 0.0004 times 2 is 0.0008 moles. Hey, that ends part C of the January 2020 Regents exam. I hope you got something out of it by going through it. I know you did. Keep working hard. Good luck. And if you haven't subscribed, please do. Leave any comments below. When it comes to chemistry, if I can help you, I'd be more than happy to do that. Good luck.